Hello online viewers, welcome to our lecture video. In this we are going to solve this problem of frame analysis. We have already solved many problems related to frame analysis, whose link you can find in this description box below. So right now we are going to solve this problem of frame analysis. Frame analysis means we are going to find our axial force, shear force and bending moment diagram. So before finding out all these forces, let me briefly describe what we are dealing with, what is our question. So right now we have UVL for our member DD, we have UVL uniformly bearing load for our member AD, and we have its value of 12 Newton per meter at joint D, while it has a value of 6 Newton per meter at our hinge C, and while it has our value of 3 Newton per meter at our joint B. And for our member BF, we have a force of 6 Newton per meter acting at E, and we have our length of member AB as 3 meter, length of member BC is also 3 meter, while our length of member CD is 6 meter. So now before finding out our axial force, shear force and bending moment diagram, firstly we need to show our support reactions. So as you can see here, in our member D we have hinge support, so we are going to only have our particle reaction, which we are going to denote it as RDY. And now for our joint F, we have a fixed support at joint F. Fixed support means we are going to have all three types of movement. First vertical reactions, then we are going to have our horizontal reactions, and finally we are going to have a moment as well, moment M. So now our first and foremost step, but before finding out all these reaction forces, is going to see whether our frame is statically determinate or not. So if you haven't seen our previous video, do see all those videos of frame analysis, so you can understand the concept of frame analysis even more clear. So right now talking about this problem, so as you can see here, so right now we have equations of equilibrium. So as you know, equation of equilibrium. So for our any frame analysis, or for our frame analysis, we are going to have three equations of equilibrium. Those three equations of equilibrium are EFX equals to 0, EFY equals to 0, and E moment equals to 0. So these are the available equations of equilibrium. These are our available equation of equilibrium. And right now we have number of unknown reactions. So number of unknown reaction, our number of unknown reaction is 1 2 3 4. So we have four unknown number of reactions. So as you can see here, right now we have four number of unknown reaction, while our available equation of equilibrium are 3. So as you can see here, r minus 3 equals to 4 minus 3, which is 1, which is smaller than 0, which means our frame is statically indeterminate. Up to this our so looking up to this our frame is statically indeterminate, which means we cannot find our value of support reactions with our three equations of equilibrium. But as you can see here, we have been provided a hinge as well. We have been provided a hinge at joint C, so our hinge is also going to add our extra equilibrium. It also going to provide one more plus one equation of equilibrium. Our hinge is also going to provide us one more equation of equilibrium. So ultimately we are going to have four equation of equilibrium. Three equation of equilibrium plus one has been provided by our hinge. So right now we have four number of unknown equation of equilibrium plus 3 plus 1, which means 1 provided from our hinge. So we have 4 minus 4 equals to 0. So right now, which means our given frame is statically determinate. It's statically determinate. So how it is statically determinate? It is statically determinate because of this hinge provided. Our hinge is going to provide us one more equation of equilibrium. Hence our this frame is statically determinate, which means we can find our value of RFX, RFY, M and RDY. So now begin our step first. So in order to begin our step first, what is going to be our step first? Step first is going to be our calculation of support reactions. So if you haven't understood yet, our hinge is provided just to give us one more equation of equilibrium. So our hinge is basically provided to give us our one more extra equation of equilibrium, so that we can calculate our support reactions. So now we have our first step is going to be our calculation of support reaction. So in our step 1, what we are going to do is we are going to simply find out our value of RFX, RFY, M and RDY. So as I have already explained in all of my previous video, you can take any sign convention for your support reaction. You can take your clockwise moment as positive, you can take your upward forces as positive, you can take your force acting at right as positive, or you can take your force acting at left as positive, you can take downward force as positive, you can take or your anti-clockwise moment as positive. You can take any of these sign conventions, but while you are calculating your shear force and bending moment, we have to follow a certain specific sign convention. But while you're calculating our support reaction, we can follow any of them. So right now what I'm going to do is, first and foremost, I'm going to take moment about F. As you can see here, right now I'm going to take my moment about F. So let me write down taking moment about F, and while I'm calculating my moment about F, I'm going to take my clockwise moment as positive. So I'm going to take my clockwise moment as positive, and as you can see here, right now in F we have already a moment. Since it's a fixed support, for our fixed support we are going to have moment. So for our so in our point F, or for our joint F, we already have a moment, and I'm going to take this as positive, since I'm assuming M to be positive, or acting in clockwise direction. So first moment about F is going to be M. Then next we are going to look out for first RDY. So as you can see, let me draw a dotted line, and let me shift this RDY in this way. Let me shift RDY downward. So right now, just to know whether this RDY is going to produce clockwise or anti-clockwise movement about F, what I'm going to do is I'm going to put one finger at a point F, and next what I'm going to do is I'm going to take this RDY from here and I'm shift it downward. So this is just going to be in your head or for your imagination person. So shift your RDY downward, and as you can see here, RDY is acting upward, and as you can see here, with respect to point F, RDY is going to push it upward. It's going to produce a upward moment, which is going to be our anti-clockwise moment. So right now we're taking our clockwise moment as positive. So since RDY is acting anti-clockwise direction, so we're going to have this as, let me put this plus minus RDY into our moment is force into perpendicular distance, and the distance from our RDY to point F is 6 plus 3, 9 meter, 9. Next what we have is next we are going to see for our portion BD, and for our member AB. As you can see here, member AB and BD, they lie at different portions. Our member AB act at left, while our member BD acts at right. So they are going to produce different nature of moments for at our point F. So what we are going to do next is we are going to divide our UVL. This last UVL we are going to divide it for our AB and for our BD. So this is a really important portion, so you need to look clearly. What I'm going to do is I'm going to draw one line in this way. So as you can see here, let me draw the figure in this way. This is going to be for my member AB. We have a force of magnitude, we have a UVL of magnitude 3 kN per meter, while for our while for our member BD, we are going to have this sort of forces. So what we are going to do is we have the magnitude of 6 kN per meter over here, and we have the magnitude of 12 kN per meter over here. So what I'm going to do next is we are going to draw one imaginary line. We are going to convert this sort of load. As you can see, this is neither UVL nor UDL. Our UVL looks like this, while our UDL looks like this. So now as you can see for our member BD, we neither have UVL nor UDL. As you can see here, our UVL looks like this. This is our UVL, uniformly bearing load, while our UDL looks like this. But as you can see, this is neither UVL nor UDL. As you can see for this portion for BD, it looks like this. It looks like this. So it is neither a UVL nor a UDL, but it's a combination of both. So what we're going to firstly do is from our point B, we are going to draw one imaginary line in this way. So imaginary line, or you can just draw a line. So this is of magnitude of 3 kN per meter. So this is also going to be a magnitude of 3 kN per meter. So the remaining is 12 minus 3 is 9 kN per meter. So our upper is going to be 9 kN per meter, our upper part. So what we have simply done for our member BD is we have converted it into a combination of UVL and UDL. So right now if you look at this portion, we have a UDL, uniformly distributed load of 3 kN per meter, while our upper portion is going to be our UVL, uniformly bearing load of magnitude 9 kN per meter. So now we are going to use this to calculate our moment about F. So this is a little bit of confusing portion. So right now what we have is for our part AB, we have a UVL of 3 kN per meter, while for our member BD, we simply have a combination of both UVL and UDL. So right now we are going to see the effect of UDL of 3 kN per meter for our joint F. So what we are going to do is so in order to convert our UDL into point load, we are simply going to multiply. So let me draw in this way. So what we simply did, we did in this way. The overall total was 12 kN per meter. So B and D, as you can see here, for our B we have been given 3 kN per meter. So going to be 3 kN per meter. It's also going to be 3 kN per meter, while our remaining is 12 minus 3 is 9 kN per meter. So firstly we are going to convert our lower UDL into point load, and in order to convert our UDL into point load, we simply need to multiply our magnitude of UDL over the span it is acting. So right now it is acting, so now our value of UDL is 3 and it is acting at a span of 9. So 3 into 9 into 9 by 2. So as I have already explained before, our UDL always acts at x over half of its span. So as you can see here, so right now I converted my UDL in this way. So suppose if this is my UDL of 3 kN per meter, which I converted it into point load, and with reference to with reference to point F, it is acting vertically downward. Vertically downward means it's producing my clockwise moment. So with respect to, so if I shift my UDL downward in this imaginary line which I dropped before, it will be in this direction of 3 into 9, which is 27 kilonewton, and as you can see here, it is acting downward and producing clockwise movement, so positive. So now after seeing my UDL, I need to look for my UVL as well. So plus UVL is also acting downward, which means it's going to produce the same bending moment as of UDL, which means clockwise moment, plus 1 by 2 into my base is 9 into my height is right now 9. 1 by 2 into 9, and it is acting at a distance of 2 by 3 into 9. So why 2 by 3 into 9? So as I have already explained before, since UDL acts over half of its span, while UVL acts at a distance of 1 by 3 from its longer span, while 2 by 3 from its shorter span. So right now we are taking our moment about B, which means we are taking distance from our shorter side. From our shorter side, if we're taking our moment about D, we will have to multiply it by 1 by 3. But right now we're taking moment about B, which is our shorter side. So right now my figure looks like this. After converting this into point load, so right now if I convert UVL, this UVL will at a distance of L by 3 from its longer span, while 2L by 3 from its longer or ending side. So right now we're taking moment from our ending or our shorter side, which means about B, which means we need to multiply it by 2 by 3. So right now we have completed our member BD. Now we need to look for our member AB. Our member AB is also going to produce some sort of load. So right now, for our member AB, we have another UVL of 3 kN per meter. So let me firstly convert it into point load. 1 by 2 into 3. 3 is my height, 3 kN per meter, while my base is 3. 1 by 2 into 3 into 3 into now for my distance. Right now I'm going to be take right. So right now I'll be taking distance from my longer side, B. So longer side of B. So right now, so in order to understand this as well, what we can simply do is we can shift this force downward. So 1 by 2 into 3 into 3, which means 4.5. 4.5 is this way. 4.5 is this way. And about F, so right now this is my load, and if I put my finger about F, it is going to push it downward, which means again anti-clockwise moment. So right now I have to take minus sign, minus 1 by 2 into 3 into 3, but this time I'm going to take distance from my longer side. So as I have been explaining before, if you cannot imagine how our RDY or how our AB portion is going to how our UVL of AB is going to produce moment, simply take those point load and push it downward. For imagination, push it downward, fix your point F and how it is turning your point about, and see what kind of movement it is producing, clockwise or anti-clockwise movement, and take your sign in that way. So right now for our member AB, it is producing anti-clockwise movement, so minus, and for our distance, we are taking a distance from our longer side. Our F is longer side. So as I explained before, for our longer side we are going to take L by 3, so into 3 by 3. So we have included all these UVL and UDL. Now our remaining last force is 6 kN. So as you can see, let me turn this figure this way. Our 6 kN is acting at a distance of 2 meter, and let me as you can see, 6 kN is acting upward. 6 kN is acting upward with respect to point F, and upward means again anti-clockwise moment. So if this is my 6 Newton per meter, and if I have my finger fixed at the point F, and if I pull my 6 kN downward, for my imagination 6 kN is acting this way, this direction, so again anti-clockwise moment. Anti-clockwise moment means negative, since I am taking my clockwise moment as positive. So finally, minus 6 into 2 equals to 0. So now I am going to get a certain equation which is going to be, so let me name this as MF, not MF, which means moment about F. This is my MF. We can simply write M or MF. So MF minus 9 RDY. If I solve all this, I am going to get my value of minus 340. It's going to be my equation first. So as you can see, taking moment is a little bit complex since there are a lot of forces involved. So you need to clearly understand what has been done for our member BD regarding the UVL and UDL. If you have any sort of queries till up to here, you can comment down below. I'll answer you there. So now what we're going to do next is, as I explained before, we have been provided Hinge for our extra equation of equilibrium, for our extra equation of equilibrium in order to find out our reaction forces. So what we're going to do next is we are going to take a moment about C. So as I explained in my previous video, joints transfer load, all our joints. So as I explained in my previous video, joints transfer moment, joint clearly transfer moment. So the moment produced at a BF at a BF is going to get transferred by B into member AB and member BD. But our hinge, they do not transfer moment. So our most important part is hinge do not transfer moment. Hinge do not transfer moment. This is a very important point. Hinge do not transfer moment, which means our moment over hinge is always going to be 0. EMC equals to 0. So our moment over hinge is always going to be 0. So what we're going to do next is, so due to our member BC, we're going to have some sort of moment at some sort of moment at moment at hinge C, but those moment is not going to get transferred to our CD portion. Similarly, due to our load acting at CD, we're going to have some sort of moment at hinge C, but our hinge is not going to transfer the moment at all. But our hinge will not transfer all those moment to CB. So right now we're going to take our moment about C equals to 0. So right now we can take our right portion, we can take CD or we can take a BC as well. Right now I'm going to take a consider right portion only. You can take a left portion as well. There are going to be no difference in answer. So considering right part only, So in our so let me draw my figure of what my right portion looks like. So from C to D, what I have is, right now I'm taking moment about my hinge C, and my moment about hinge is always going to be 0, since hinge is never going to transfer my moment from left to right or from right to left. So this is my C and this is my D. So this is what my figure looks like, C and D, and I have my RDI over here, and I have this sort of a load arrangement. This is going to be 12 kilonewton per meter, and this is going to be 6 at C. The magnitude of UVL is 6 kilonewton per meter. So let me write down this way. So while calculating our moment, we got a certain condition for our BD where we did not have the load of nature UVL or UDL. So again we have come up with the same problem. We neither have UDL nor UVL. So again we are going to draw one more imaginary line. This is a combination of both UDL and UVL. So we are going to draw one imaginary line, and this is also going to be 6 kilonewton per meter, and our remaining this upper portion is 12 minus 6 is again 6 kilonewton per meter. So right now this is a combination of both UDL and UVL. So right now also we are going to take our clockwise moment as positive. You can take your anti-clockwise moment as positive. You can consider any sort of sign convention while calculating your moment. So now considering right part only. So firstly what we have is, we have a UDL, uniform distributed load of 6 kN per meter, acting at a span of for our CD we have a span of 6 meter. So this is going to simply into and our UDL both are acting, UDL and our UVL both are acting downward means about points they're going to produce clockwise moment. They're going to produce clockwise moment, which means they are going to produce clockwise moment. So I'm going to take my direction as positive. So firstly, in order to convert my UDL into UVL, 6 into 6, span is always half, 6 by 2 as I explained before. 6 kilonewton per meter UVL acting at a span of 6 meters. So 6 into 6. Now for my distance, I simply multiply 6 into 2 plus 1 by 2 into base is 6 into my height is again 6 kilonewton for my UVL. And right now I'm again taking my distance from my shorter side. Since I'm taking distance from my shorter side, I'm going to multiply it by 2 by 3 into 6. So I've already explained this before. Plus so now minus, now RDY is acting upward with respect to point C, and upward means it is producing anti-clockwise moment. It is trying to push my beam upward with respect to point C. Upward means anti-clockwise. Minus RDY into 6. So if I solve this, RDY into 6 equals to 0. So if I solve this, I'm going to get my value of RDY, which is going to be equal to 30 kilonewton and 30 kilonewton. And if I substitute my value of RDY in equation number 1, I'm going to get my value of MF, which is my moment about F, and my MF is simply going to be equal to minus 78 kilonewton per meter. So right now I got my direction of MF as negative, which means it is going to be hogging bending moment. Negative means hogging bending moment. So right now I have I suppose my direction as clockwise as positive. So this is not my correct sign for MF. My MF is actually acting in this direction, opposite. It is acting in opposite direction as I suppose. So right now we found our value of MF and MF and RDY. Next we need to find our value of RFY and EFX. So what we're going to do next is we're going to take all the forces acting in upward. So let me do it over here only so that we can be clearer. So right now what I'm going to do next is I'm going to take upward forces as positive and EFY equals to 0. So right now I have RFY acting upward, RDY acting upward, RFY is acting upward, RDY is acting upward, and next what I have in vertical force, next I have other force acting in vertical direction is my this UVL, which is minus 1 by 2 into my total span is 6, 7, 8, 9, 10, 11, 12 into 12 into its magnitude is 12 equals to 0. This is equal to, I have my value of RDY as 30, so RFY plus 30 minus 12 into 12, 144 divided by 2 equals to 0. So I am going to simply get my value of RFY as RF. So now I'm going to get my simply value of RFY was 42 kilonewton. So what I have simply done is I have taken this complete UVL. So right now I'm not going to take any moment. So what I can do is I can simply convert this complete so I can simply convert this complete UVL into point load, directly into point load. So now next what I need to do is I need to find my RFX. So I'm going to take forces acting at right as positive, EFX equals to 0. So as I explained before, we have already used all three equations of equilibrium, EFX, EFY, EM, and we even used our moment, we used our Hinge C, taking moment over Hinge C as 0 for our extra equation of equilibrium and taking EFX equals to 0. So forces acting at in X direction. So as you can see, we have only one force, EFX acting at right, minus 6 is acting in left. So right now I'm taking forces acting at right as positive, so it's going to be minus 6 equals to 0. So simply the value of RFX is going to be 6 kilonewton. So we have now complete our step first, which means we have calculated all our support reactions. We have calculated all our support reactions. So as you can see here, as I explained before, our frame is statical determinant. So in this way our frame is statical determinant, because with our available equation of equilibrium plus 1 from Hinge, we have found out all of our support reactions. So next we are going to find our axial force and shear force diagram. So before moving into our step 2, this is going to be calculating our axial force, shear force and bending moment diagram. What we are going to firstly do is we are going to draw all our members, and we are going to write down all the forces which we have calculated yet. So let me draw my 3 members. So as you can see here, firstly I have my member BF, AB and BD. So let me put down all of those. This is my member BD, this is my member BF, and this is my member AB. So let me write down all the forces which I have calculated. So what we found out was, we found RFY we found as 42 kilonewton. So let me write down this way, RFY equals to 42 kilonewton, while my RFX is found to be equal to 6 kilonewton. And I found the moment over F as well. I initially took my moment, I suppose it as clockwise, but it was found to be anti-clockwise since I got direction negative. So minus 78. So I have got this moment 70 kilonewton meter. So next what I am going to do is, so next I have found my value of RDY as well. RDY is equal to 30 kilonewton. So right now these are all the forces which I have calculated, and we have been provided a Hinge C, internal Hinge C, and as you can see here in our point E there is a force of 6 kilonewton. This is my point E. A force of 6 kilonewton is acting upward. So now let's see firstly for my member BF. As you can see, for my member BF, a force of 40 kilonewton is acting upward. So in order to maintain equilibrium, what needs to happen is a force of 40 kilonewton must act downward. A force of 40 kilonewton must act downward. But as you can see again for my member BF, 6 kilonewton is acting downward, but already there is a force of 6 kilonewton acting upward. So both these forces gets cancelled out. So there do not need to be any sort of extra force or extra additional force at our joint B. So this is already in balance in the x direction. But for our y direction, 40 kilonewton is acting upward for our member BF. If you do not have any sort of force acting downward, this our member BF will get pushed upward. So in order to maintain equilibrium, a force of 40 kilonewton must act downward. So now after putting your force of 40 kilonewton downward, we are going to show our other force as well. For our member AB, we have our UVL of 3 Newton per meter acting at a span of 3 meter, which means 1 by 2 into 3 into 3 acting downward, which is 9 by 2, which means 4.5 Newton acting downward. 4.5 Newton acting downward. Similarly for our BD as well. We have BD as well. We have a combination of both UVL and UDL, which is our this much is 3. So as I explained before, this is going to be 3 into span of 9. So 3 into 9 divided by 2, plus we have going to have 12 minus 3 is 12 minus 3 is 9. 1 by 2 into 9 into 9. So let me tell you what I have done. So right now we are going to have two more forces for our member BD. So firstly we are going to have one force. So we're going to have one force and it's going to be other force. We're going to have two sort of force. This first force is going to be 1 by 2 into it's going to be 1 by 2, which is at a distance of 1 by 2. So we're going to have our it's going to be my UDL, which is going to be 1 by 2 into 3 into span of 9. 1 by 2 into 3 into span of 9. 1 by 2, 3 into span of 9. So 12 minus 3 remaining is 12 minus 3 is our 9. 1 by 2 into 9 into 1 by 2 into, so I have simply converted my UDL into point load. So there only 1 by 2, sorry, there only 1 by 2. In order to convert my UDL into point load, I simply need to multiply my magnitude of UDL over its span, which is simply going to be 3 into 9. Next I am going to convert my UVL into point load, so I am going to multiply it by 1 by 2 into 12 minus 3 is 12 minus 3 remaining is 9 into 6 plus 3 is 9. So again the same concept as I explained before. It's going to be 81 divided by 2 and it's going to be 27 kilonewton. 27 kilonewton, and 81 divided by 2, this is going to be 40.5 kilonewton. So I have so now in order to maintain equilibrium, as I explained before, 4.5 kilonewton is acting downward. So in order to maintain equilibrium at our joint B, a force of 4.5 kilonewton must act downward. 4.5 kilonewton must act downward. So as I explained before in my previous videos, so for a member BF, I have my 12 kilonewton acting downward. So in order to maintain equilibrium, a force of 42 kilonewton must act upward. A force of 42 kilonewton must act upward in order to maintain equilibrium. But this force of 42 kilonewton will get divided into two portions. This 42 kilonewton will get divided for my member AB and for my member BD as well. In our previous cases, we used to have only one member. So if we have 42 kilonewton acting the downward for our member AB, if we did not had our member AB, let's say we don't had our member AB, then we can directly put our force of 42 kilonewton acting downward for our member B in here. But right now we have two members, member AB and member BD. So this 42 kilonewton is going to get simply divided into two portions. It's simply going to get divided. So right now we have 4.5 acting upward. So we will usually have 4.2 kilonewton acting upward. So 4.2 minus 40 minus 4.5. This is going to simply be equal to a force of 37.5 kilonewton acting downward. And if you do this as well, you are going to simply get 40.5 plus 27 minus 13. This is also going to be equal to 37.5 kilonewton. So simply in order to maintain equilibrium, a force of 37.5 kilonewton must act at B. So if you can do it this way as well, 40.5 and 27 down minus 30, which means 37.5 kilonewton must act upward in order to maintain equilibrium. Or simply as I explained before, since the force of 42 kilonewton is acting at joint B downward, so this is going to be same joint. These are our same joint B. So this 42 kilonewton simply gets divided into two portions of 4.5 and 37.5. 37.5 plus 4.5 is simply equal to 42 kilonewton. 42 kilonewton. So right now we have this sort of forces. Next we'll be calculating moment and we'll be distributing our moment in this way as well. So firstly now I'm looking for my member BF and I'm going to calculate my shear force and bending moment and axial force for my member BF. So right now for my member BF, firstly what I'm going to do is, so as I didn't explain before, but since overall frame is in equilibrium, we're going to suppose our overall frame is in equilibrium. Since our overall frame is in equilibrium, our member AB and member BD and our member BF are also going to be in equilibrium. So firstly we're going to consider our member BF and we're going to consider equilibrium of member BF. So first we're putting down all of your forces in this diagram. Next we're going to calculate our axial force, shear force and bending moment diagram. So firstly we are going to consider our member BF. So I did not say this before of the video, but right now we're considering our overall frame to be in equilibrium. We're considering our overall frame to be in equilibrium. Since our overall frame is in equilibrium, our member BF, our member AB and our member BD, our each and every member also must be in equilibrium so that our overall frame is in equilibrium. So right now we're going to consider our equilibrium of member BF. So our first and foremost step is going to be, so after doing this we're going to consider, so right now let me write over here, consider equilibrium of member BF, and we're going to draw our figure of member BF. So right now we have this way, we have our figure in this way, so we're going to draw this figure. So for our member BF, we have a force of 40 kN acting upward and a force of 40 kN acting this way. Next we have a force of 6 kN acting over here, and for our at our point E we have 6 kN acting upward. So this is our overall forces acting at our point, acting for our member BF. So firstly we're going to calculate our axial forces. So what are our axial forces? Axial forces we're going to denote is as NBF. So right now we are moving from left to right. So for our axial forces are simply those forces which act along our member or parallel to our member. So for our member BF we have only one force, 42 kN acting inward. So as you can see here, this 42 kN we are going to take this as minus 42 kN. So why minus? Because this is compressive, because this is of compression in nature, compression. So as you can see here, this 42 kN is pushing our beam inward. They are pushing my member BF inward, and they are producing compression. So axial force NBF is simply going to be minus 42 kN. So next we are going to calculate our shear forces. Shear force. So shear force are simply those forces which act perpendicular for our perpendicular along our member. So we can calculate our member by taking a certain section x or directly as well. So right now I'm going to do it directly. For our other member we're going to be taking a certain section x. So as I explained before, while calculating our movement we could take any sort of sign convention. We could take a clockwise movement as positive, anti-clockwise movement as negative. But while calculating our shear force, we need to follow a certain set of sign convention. So if we are moving from left to right, we are going to take our upward forces as positive, while our downward forces are going to be negative. While we are moving from right to left, it is going to be exactly vice versa. Upward force negative, downward force positive. Similarly for our bending moment, while we are moving from left to right of the beam, we are going to take our clockwise moment as positive, while our anti-clockwise moment as negative, while vice versa moving from right to left. So right now we are moving from left to right for our member BF. So our shear force about B. So first we are going to write down our shear force. Now we are going to calculate shear force for our member. So there's a mistake. This is joint B. This is joint F. So we're going to calculate our shear force for my member BF. So as you can see here, I have my point F downward and B upward. I had initially write down in opposite way, so you can call it that. So I have my joint F down and joint B up. So firstly we're going to calculate my shear force about F. So shear force about F, BF is going to be minus 6 kN. So let me explain why minus 6. As you can see here, right now I am moving from F to B. So since I explained before, while moving from left to right, upward force are negative and downward force are negative. This 6 kN is acting downward, which means negative. So I am going to simply write my shear force about shear force at F. BF is simply going to be minus. Next I am going to take another point at left of E. Left of E is also going to be minus 6 kN, because from F to E at left of E, which means it is going to be somewhere over here. There are no sort of other forces acting vertically along our member BF. So next I have VVR, which means right of point E. This is going to be 0 kN. So by 0, 6 minus 6. So as you can see here, as I move right of E, I have 6 kN acting downward, and as I move right of E, I have 6 kN acting upward. Since upward force are taken as negative, minus 6 plus 6 equals to 0. So shear force at right of E is simply going to be 0 kN. And now finally at point B, VV is also going to be 0 kN, because there are no sort of any other forces acting. Up to B there are no sort of any other forces. Now next we are going to calculate our bending moment. So this is our sign convention for bending moment. I have already explained it about. it. Now for our bending moment. So in order to calculate our bending moment, first we are going to take a certain section. Take a section x. We're going to take a certain section. So let me draw my figure this way. So F, this is my B. So 42 F 6 kN, and at point E. And at point E this is 6 kN. So I have simply drawn my figure this way. So in order to take our section XX, many students have confusion where to take our certain section XX. So right now we are going to take our certain section XX over here. But why here, why not here? So as you can see here, we need to take our section at two different point, at up to here and up to here. Let me explain why. So firstly, let me take my section over here and let me calculate my moment. So taking moment, so my bending moment mxx is simply going to be equal to, so bending moment is simply product of product of force and perpendicular distance. So what we have been missing over here is we have a force, we have a anti-clockwise moment of 17 km. So which we have calculated this moment we have been missing. So let me write down it over here. We have missed this before. This moment do not have any effect in shear force and axial force. It will come into play only for our bending moment. So at over here we have anti-clockwise moment of 78 kN at our joint. Yeah, 78. So right now we are going to take a moment up to this section, up to this section. So up to our certain section xx. So we are going to look out for our forces. We have 78 kN moving anti-clockwise. As I explained before, anti-clockwise forces are taking negative, so minus 78. And next we have 6. So with respect to our certain section xx, so let's say this my pin is my certain section xx, 6 kN is acting downward. So this is at a distance of x, it is acting downward. Downward means it is producing, with respect to my certain section xx, it is producing anti-clockwise moment. Anti-clockwise moment means negative, minus 6 into my distance is x. Why negative? Because while moving from left to right, clockwise moment is positive, while anti-clockwise moment is negative. So now we are going to put our value of x. So when x equals to 0, meter, I have my moment about f, which is going to be minus 17 kN per meter, which is true because I have only one moment about f, which is 17 kN per meter acting anti-clockwise, negative. When x equals to, next I'm going to take a point at a distance of, so my overall distance of fb. So let me see my, so from our question, as you can see here, my overall distance of fb is so my overall distance of fb, so I have missed this distance as well. Okay, so my overall distance of fb is 4 meter. So I have missed to give this before. So my overall distance is 4 meter. So my overall distance is 4 meter over here. So let me, so this is my 4 meter. So let me take another point, and this is e as a e is at a distance of 2 meter. This point E is at a distance of 2 meter. So let me take my x equals to 2 meter. When x equals to 2 meter, I reach my point E. Moment about E equals to minus 78 minus 6 into 2, and I get my this value as minus 90 Newton per meter. So now, as I move right of E, after when, so let's say when I take x equals to greater than 2, which may be 2.1, 2.2, or right now I'm going to take 4 meter, which is going to be at point B, moment about B. What you can see is, as I move right of E, or as I increase my distance from 2 meter, as I move right, what you can see is now I have another new force, 6 kN. I have my new force of 6 kN, which means I have to take another section xx. So hope you have understood why I was explaining we need to take certain two sections, because we have two different loads. One load is acting downward, but while my another load is acting upward. But this load of 6 kN per meter will have no any sort of bending moment produced at for our this portion. This 6 kN per meter, this 6 kN is not going to produce any sort of moment at F, and for the point E as well. And for the point E as well, there is not going to be any effect of 6 kN. But as I move right of E, this 6 kN is going to produce moment, and it is going to produce clockwise moment. So which means positive. So as you can see here, up to here, so up to this section there was no use of 6 kN. So right now for our moment we did not include our 6 kN, but as we move right of E, the 6 kN is going to produce some sort of moment. Is our clockwise moment, so we need to include this as well. So for our, now we're going to take our another section. So our, let me put it over here, mxx is going to be simply equal to, so this now we're going to take our section x up to here. So this is going to be our new section xx, and is going to be it is at a distance of x from my point F, and I have minus 78 minus 6, this is at a distance of x, so 6 into x, and my and this 6 is at a distance of x, so minus 6 into x, while this 6 is at a distance of x minus 2. So this distance is, this overall distance is x, and this is 2, so this remaining distance is going to be x minus 2. So plus, it is producing clockwise moment, so plus 6 into x minus 2. So it's going to be my equation. So I'm going to put my 4 over here, minus 78 minus 6 into 4 plus 6 into 4 minus 2 is 2. So minus 78 minus 6 into 4 plus 6 into 2, and I'm going to get my this value and now I'm going to get my this value as again minus 98 kilonewton per meter only. Minus 90 kilonewton per meter. So hope you have understood why we need to take two sections, because before point E there was no use of this 6 kilonewton, but at point E this 6 kilonewton is going to produce your clockwise moment. So we need to have a different moment, a different equation of moment. So now we have completed our member BF. Now we are going to look for our member AB. So now we are going to consider for our member AB. So we have already done our figure for a member AB. So now as we did for a member FB, now we are going to consider equilibrium of member AB. Consider equilibrium of member AB. Consider equilibrium of member AB. So let me draw my figure for member AB as well. So I have in this way 4.5 kilonewton, and at this is my B, this is my A, and 4.5 kilonewton acting upward. So firstly we are going to calculate our axial forces. So as you can clearly see for member AB, there are no sort of axial force, because there are no sort of force acting along our direction AB. So simply axial force and AB equals to 0 kilonewton. Next is our shear force. Yes, F. So in order to calculate our shear force, we are going to move from A till B. So as you can clearly see, so as you can see here, we have in our question originally we had a UVL, uniformly bearing load. We had originally a uniformly bearing load. So let me draw that as well. So this is my member AB, and we had a uniformly bearing load. This is acting at a span of 3 meter, and we had the force of 3 kilonewton per meter. So this is I'm simply writing down my question. So this is what my question look like: 3 meter, 3 kilonewton per meter for my member AB. So right now I need to calculate my shear force. So this time I need to take a certain section XX. So let me write down, taking a section XX. Whenever we have UVL and UDL, we must take our certain section. We need to take a certain section XX, like we did for bending moment, to make our work easier. So while taking our section XX, I'm going to take my certain section XX in this way. Certain section XX, and this certain section XX is at a distance of X. So let me assume the value of UVL at this point as WX. So we need to find while calculating our shear force, we are going to need this value of WX. So right now over here at point B we have our value of UVL, which is our highest value, is 3 kilonewton per meter. But right now at this point, so we'll not be looking this point while calculating our shear force and bending moment. We'll be looking at this point. So we need to find the value of this WX. What is the magnitude of UVL at this point? So we have supposed it at WX. Now what we're going to do next is we're going to simply use our similar triangle method. So as you can see, this is our bigger triangle and this is our smaller triangle. So we have WX divided by X equals to bigger triangle 3 divided by 3. So we're going to simply get our value of WX as 1. WX equals to X. So our magnitude of WX is simply going to be X. So taking a certain section XX, we need to calculate our shear force. So shear force Px equals to shear force Px. So right now we are moving from left to right. So while moving from left to right, forces acting upward are positive, forces acting downward are negative, So while moving from left to right, we have only one sort of force till our certain section XX. So we're going to look up to here only, not look backward of it. So up to here only we have only one force of WX acting downward. So let me draw my figure this way. We have just one WX which is acting downward at a distance of X. This is my certain section XX. So this is going to be simply equal to minus 1/2 into WX into X. I have simply converted my UVL of WX into point load. So minus 1/2 into my value of WX is X into X. My WX is X. Minus 1/2 into X into X. So simply going to be equal to minus 1/2 X square. Now I am going to simply put my value. When X equals to 0, I am going to get my shear force about A, which is 0 kilonewton. When X equals to 1.5 meter, so the overall span is 3 meters. So I am going to take my another shear force at half. V 1.5 equals to minus 1.125 kilonewton. while my x equals to 3 meter, I am going to reach my point B. Vv is simply going to be equal to minus 4.5 kilonewton. So next, after calculating my shear force, I'm going to calculate my bending moment. For my bending moment as well, I need to take my shortened section x. I'm going to take my same section. So my bending moment m xx is simply going to be equal to, so right now I am moving from left to right. Do not see the section behind of xx, so just see the section before of xx. I have my wx, I have my UVL of wx. Let me see this figure. UVL of wx acting downward. So if I convert it into point load, so this is my wx, and this is my shortened section xx. So let me explain in this way. This is my shortened section xx, and the total distance is x. So which means this wx will act at a distance of x by 3 from my shortened section xx and 2x by 3 from its shorter side. I will explain this before. X by 3 to x by 3. So this wx with respect to xx is going to produce anti-clockwise moment. So as you can see here, it is pushing downward. Downward means anti-clockwise moment. So simply put this way, minus 1 by 2 into wx into x. I have converted into point load, and it's at a distance of x by 3. X by 3, so it's going to be simply equal to minus 1 by 2 into x into x into x by 3 is going to be x cube minus minus x cube by 6. So when x equals to 0, when x equals to 0, I'm going to get my moment about a. My moment about a is going to be 0. So when x equals to 1.5, my moment about moment at a distance of 1.5 will be simply equal to minus 0.5625 kilonewton meter. Finally, when my x equals to 3 meter, I'm going to reach my point B, and I'm going to get my value of moment as minus 4.5 kilonewton per meter. So now I have completed my bending moment as well. So now let me move on to my this figure. So as I explained before, this force of 42 kilonewton at joint B got divided. So right now, so before that, so I did not add this, but I got a bending moment of minus 90. So let me put it this way. I got a bending moment of minus 90, which means anti-clockwise, which means minus 90. Minus 90 means this way, minus 90 kilonewton per meter. So now we have taken our direction of bending moment at B in this way, in our anti-clockwise direction. So let me explain why we have taken this in anti-clockwise direction, because right now we have here hogging bending moment because of negative direction. So let's see if we have a beam AB. I have already explained this in my previous videos, but let me explain this in this video as well. So if my beam moves downward in this way, it's called as sagging, while if my beam moves downward, it's called as hogging. For our sagging bending moment, I'm going to have this sort of moment, while for my hogging bending moment, I'm going to have this sort of moment. Our sagging bending moment is considered as positive, it's my sagging, while my hogging bending moment is considered as negative. This is my sagging, this is my hogging. So as you can see, this is my sagging, this is my hogging. So if my beam moves this way, this is sagging, while my beam moves downward, is hogging. So in sagging, while moving from left to right, I have my clockwise moment, while at my right I have my anti-clockwise moment. So right now I have my hogging bending moment. So in my hogging bending moment, this is my negative, and right now I'm going to have anti-clockwise moment at right side. Anti-clockwise moment in this sort of moment. So as you can see here, since I have my negative bending moment, which means hogging, so right now I have shown my direction downward, following this downward hogging. In case it was sagging, or if I had positive bending moment, I'll be showing it upward in this way. So, but right now I have hogging, so downward. So next, now I need to look for a member AB. I have got hogging bending moment as well, hogging, which means minus 4.5. So minus 4.5. So as you can see, if this is my member AB, minus 4.5 means I'm going to show my direction in this way. For sagging, but right now I have hogging, so this is my member AB. So for my hogging bending moment, I'm going to show my direction downward at right portion. This is my minus 4.5, or you can simply put 4.5 as well. So now, as I explained before, our joint is going to transfer moment. Joint transfer moment is my very important point. Joint transfer moment. Our hinge do not support moment. This our point C. This hinge is not going to transfer our moment, but our joint B is going to transfer our moment. So right now, as you can see here, it has got a little bit messier, but right now I have got minus 90 kilonewton, minus 90 hogging bending moment at joint B. So this hogging bending moment is going to get divided. It's going to get divided for member AB and a member BD, like our 42 kilonewton got divided. So like our 42 kilonewton got divided into 4.5 and 37.5. This hogging bending moment of minus 90 is also going to get divided. So I have already got 4.5 over here. About for our member B, now for our member BD as well, we're going to get certain moment. So in order to calculate this moment, what we can simply do is instead of simply dividing minus 4.5, we have minus 90. So as you can see, we're going to get minus 94.5. Minus 90 minus 4.5 is minus 90 minus 4.5. We're going to get minus 94.5 kilonewton meter. But right now, in order to calculate our moment for BD, we're going to do it in this way. For member BD, we have to find our moment. We are going to get certain hogging moment, because this hogging moment 90 is going to get distributed 4.5 and 94.5. We can simply do this directly, or in order to find this, as what you can do is you can take your member BD and let me write down the moment, this moment as M. This is going to be simply equal to, you can simply take the forces all over here, 30. This is my 30. This is going to produce my clockwise moment. And this is acting at a distance of 9 meter. So let me minus 94 points. So let me show my initial figure. So you can see here, this is my initial figure, and I have this RDY acting at RDY, which is 9, is acting at a distance of again at a distance of 9. This RDY, which is equal to 30 kilonewton. This RDY, which is equal to 30 kilonewton, is acting at a distance of 9. So 30 into 9 minus 3 into 9, this 27 kilonewton. This 27 kilonewton is acting at a distance of 9 by 2. Since this is a uniformly distributed load, it always acts half of its span, 9 by 2 again, minus 1 by 2 into 9 into 9, which is this force 40.5, but this time the distance is 2 by 3 into 9, 2 by 3 into 9, because the distance is from shorter side. So I'm going to this on solving this, I'm going to get my value of minus 94.5 kilonewton per meter, which is hogging. So I would suggest you to do this, this 90 kilonewton meter gets divided for both this portion, which is 4.5 for this portion and 94.5 for this portion. So in this way we can calculate a moment for our both of those joints B and D. So now we are going to consider equilibrium for our member BD and calculate all our forces. So now this is our member BD. So first we are going to draw our figure BD. So let me draw my figure BD first of all. So again for our member BD, we have our combination of both UDL and UVL, and at D we have our value as 12 kilonewton per meter, while at B we have our value as 3 kilonewton per meter. So again we are going to take our certain section, and we have so let me show you my figure. Again we have moment as well. We have moment about B as well, minus 94.5 kilonewton meter, and again we have a force about D as well, which is 30 kilonewton per meter, and we have another internal hinge C, and this is acting at a span. This overall BD, this is acting at a span of BD is acting at a span of 9 meter, and this internal hinge C is at a distance of 3 meter from point B. So now we are going to solve this. So before that, first we are going to consider, so let me write it this way, consider equilibrium of member BD, consider equilibrium of member BD, and first we are going to calculate our axial forces, axial force. So our axial force NBD is simply going to be equal to 0 kilonewton meter. So after that, for our shear force, as I explained before, if we have a combination of if we have any UDL or UVL or a combination of both, we are going to simply distribute in this way. We are going to draw our line this way. This is going to be 3 kilonewton per meter, and our remaining this is going to be equal to 12 minus 3 is 9 kilonewton per meter. So what we are going to do now is we are going to take a certain section. We are going to take a certain section XX. So we are going to take a certain section XX in this way, and we're going to assume the value of the UVL over here as WX, and as before we're going to simply use a similar triangle concept. WX divided by X equals to we're going to take this upper UVL only. Our UVL is 9 divided by our UVL is acting at a total distance of 9. So again WX is simply going to be equal to X. So hope you have understood how this is done. We are looking for our UVL portion only. UVL portion, and our magnitude of UVL is 9 kN per meter, 9, which means 9 divided by span is again 9 by 9 this way, while our smaller triangle consists of UVL of magnitude Wx. This is going to be my Wx divided by the distance of UVL is x. This distance is x. The smaller triangle and the bigger triangle, Wx by x equals to 9 by 9. So Wx is simply equal to x. So now we are going to solve for our shear force diagram. So we are going to take shear force Bxx equals to, so right now we are moving from left to right, and as you can see here, we have missed one more force over here. So at B we have 37.5 acting upward, 37.5 kilonewton acting upward. This 37.5 kilonewton is acting upward at B. So now while we are moving from left to right, we are going to see up to our starting section XX. So I am keeping my pen over here, and as you can see here, while moving from left to right, first we have our 37.5 kilonewton acting upward, which means positive 37.5 minus. Why minus? Because now we are going to look for our UDL of 3 kilonewton meter. 3 kilonewton meter, it is acting at a span of x, 3 into x. So simply 3 into x minus, now again minus 1 by 2 into 1 by 2. Now we are going to look for our UVL, which is acting at a span of which has magnitude Wx, magnitude Wx, and it is acting at a span of x, and this which is acting at a span of x. So we don't need to multiply by distance for shear force. So it's going to be simply equal to 37.5 minus 3x minus 1 by 2 into x. I'm going to this my value as 37.5 minus 3x minus x square by 2. So hope you have understood shear force. So if you have understood till this part of the video, and if you are liking our, subscribe our channel and like our video. So moving on, when x equals to 0, I'm going to get my shear force about B, which is going to be 37.5 kilonewton. Simply put 0 over here. When x equals to, now I'm going to take at 3 meter, which means I get my shear force at my internal hinge C, and this value is going to be equal to 24 kilonewton. Next I take my x as 9 meter. When I take my x as 9 meter, I'm going to reach as VD. I'm going to get this much as minus 30, and if I move right of D, I'm going to get my shear force as minus 30 plus 30, which is going to be 0, because I have a 30 kilonewton meter at the D and it's acting upward. So positive minus 30 plus 30 equals to 0. This part is optional, you can put it as well. So this is as a check. At our shear force at the end must be 0. So if I had got something else like 31, 32 or 40, 20, it's going to be incorrect. So 30, so I have 30 over here, and I exactly got 30 acting downward, which means minus 30 plus 30, shear force at right of D is 0. So now after doing this, we are going to take our moment, bending moment, M x to M xx equals to, so again we are going to take our certain section xx, and we are going to look up to it. So firstly I have minus 94.5, so let me put that first of all, minus 94.5. Now we are going to look for our 37.5. With respect to this pin, which is our certain section xx, 37.5 is moving upward, which means producing clockwise moment, plus 37.5 into x. Now again for our 3 kilonewton, it is again producing my anti-clockwise moment. This UDL, this downward UDL, this UDL is producing my anti-clockwise moment because it is acting downward. So minus 3 into x, the magnitude, simply this magnitude, and simply copied it over here, into now it's acting at a distance of x by 2. Now finally for my UVL, minus 1 by 2 into Wx into x, the magnitude I have copied it from up. Now for my distance, from this distance it is acting at a distance of x by 3 from its longer edge. So as you can see here, this way it is acting from this section xx, which is at a distance of x by 3. This is my Wx. So 1 by minus into x by 3. So on solving this, I am going to minus 94.5 plus 37.5 into x minus 3x square by 2 minus 1 by 2 into x cube by 3. This is x, so x cube by 3. So now I'm going to simply put up my values. So when x equals to 0, I'm going to get my bending moment at B, and my bending moment about B is minus 94.5 kilonewton per meter. Next, when I put my x equals to 3 meter, I'm going to get a bending moment about C, which is bending moment about internal hinge is always going to be 0. So this is as a check as well. If I had got something else than 0, my equation will be wrong. When x equals to 6 meter, I'm going to get my bending moment at 6 meter equals to bending moment at 6 meter, and when x equals to 9 meter, I'm going to get my bending moment at D. So simply my value is going to be 40.5 and 0 and 0 over here. So what we could have done is we could have taken one more at 6 meter. So right now we are going to take at a half at one more point, so that we can draw our shear force and bending moment easily. So when x equals to 6 meter, I get m 6 meter equal, I get my v6 equals to 1.5. We can do this one more point. You can add one more point for your shear force as well. So now we have calculated our shear force, axial force, and bending moment for each and every member. So now next we are going to draw our axial force diagram, shear force diagram, and bending moment diagram. So now we are going to draw our axial force, shear force, and bending moment diagram. So simply we are going to draw our all the members in this way. This is going to be for a member. So this is going to be for a member BF, and let me draw one more line. This is my A, this is my B, this is my F, and I have my E over here, and this is going to be my point. This is going to be my point D, and this is going to be my point C of internal hinge. So B, C, D. So I have simply drawn this. So let me draw this two more. One over here and one more over here. Point A, B, C, D, E, F. A, B, C, D, E, F. So this is going to be my axial force diagram. So let me so if you remember, for a member BF, I found my axial force equal to minus 42 kilonewton. So I'm going to draw my axial force in that way. Minus 42, I'm going to draw downward minus 42. Negative, this is minus 42 kilonewton. My axial force diagram is complete because my axial force about AB and AB and BD member are 0. So next, this is my shear force diagram. So now to draw my shear force diagram, firstly I'm going to see for a member. Firstly I'm going to see for my member BF. So as you can see here, for my member BF, I found shear force as minus 6, 0, and again 0. So my shear force about F is minus 6. So I'm going to put minus over here, minus 6, and as it reached point E, it got 0. So my shear force diagram is going to be this way. Shear force at E is again 0. So put minus sign, minus 6 kilonewton. So for a member BF at above this point, it is again 0. So this graph continues this way. This is my minus sign. So for a member BF, minus 6, 0, 0. So minus 6 is again minus 6 kilonewton and 0. Now for a member AB. So as you can see, for a member AB, I got my shear force as 0, minus 1.25, minus 4.5. So let me draw my member AB a little bit farther. Initially I got my value as 0. Then it was minus 1.25 and minus 4.5. So minus 1.25 and minus 4.5, minus 4.5 kilonewton. And as you can see here, I have my whole square in my shear force formula, which means my nature is going to be parabolic. It's going to decrease this way. This point is minus 1.5. Make sure it looks parabolic. Do not draw your shear force diagram linearly. Do not draw this way. Draw this way. Draw this way. So shear force diagram is completed. Now shear force diagram for my member BD, I have got my shear force as 37.5, 24, minus 30, 0. So at B is 37.5. So let me draw straight line, positive. So I'm going to draw my positive upward. I have drawn my negative downward and a positive upward. Same for my axial force as well, 37.5 kilonewton. And next I have at C I got 24. At C I got 24. Again parabolic, because as you can see here, I have x square in our formula. So draw it parabolically. But parabolic this way or parabolic, but we need to draw parabolic, but parabolic this way or parabolic this way. So this is a major confusion among many students, and many teachers do not explain this. But let me show you why. As we have, so let me explain it over here. So if we have like this, we can have your shear force drawn in two ways. First diagram drawn in two ways. So let's say you can draw a shear force in this way as well, or you can draw your shear force this way as well. So right now I have chosen, so when this and when this, so simply you need to draw your slope. You need to draw your slope. As you can see here, the slope of this curve is more, slope is more, while the slope of this is less, and our slope is directly proportional to our intensity. And if we're talking about B and our C, let's say, and this is my B part, this is my C part, this is my B part and C part. As you can see here, at B part my intensity of the load is less, while at my C part intensity of the load is high. If so, which means slope is directly proportional to intensity, which means for this here, for this figure, while I'm moving from B to C, I'm going to have this sort of figure. Well, where the slope is less at point B because intensity is high. So as you can see, we do not draw this figure, but we draw this figure. So for this question as well, I have this sort of arrangement, which means I have less load at B, which means I'm going to draw figure this way with less slope, because of less intensity. So I have drawn wrong figure. So let me draw this way. So let me do the correction. Hope you have understood why I did the mistake, in order to explain you how you need to draw your shear force diagram as well. Many people just draw it randomly this way or this way, but you need to understand that the slope is directly proportional to your intensity of the load. So you need to draw it that way. So after minus 24 for my member BD, I have got minus 30 and finally 0. It is a distance of 9 meter, which is at this point, which is exactly at point D. I'm going to get minus 30. So let me draw this way. Let me complete my figure. So right now I have drawn this nature of curve, which has less slope because of less intensity, because my figure looks like this. If I had this sort of figure, I'll be drawing this way. Because of my intensity. So let me put on positive sign over here. It's going to be my negative sign. It is 24 over here, and it is minus 30 kilonewton. So my shear force diagram is also completed. So as you can see here, this analysis of frame consists of many idea and concepts. So I have been explaining it step by step. So if you like our video, so if you like how I am explaining, to subscribe the channel. So now finally for our bending moment. So firstly, I'm going to begin with my member BD. For a member BD, I have my bending moment of minus 94.5, 0, 40.5 and 0. So at B it is minus 94.5. So over B I have minus 94.5. Next I have at C I have a 0. So I'm going to decrease this way. Since this is a cubic function, it's going to follow my cubic nature, 0 cubic function, so it's going to follow 0, and at 6 is 40.5 and 0. So it's going to reach at 6 meter, which is somewhere in the middle, and then 0 at D is positive, this is negative, this is 0, and this bending moment is equal to 40.5 kilonewton per meter. So as you can see here, right now I have taken my negative at up of the beam and I have taken positive down. So let me explain why. So if this is my normal beam, if my beam moves in this way, it is considered as sagging. So right now my beam has moved downward and sagging is considered as positive, while if my beam moves upward in this way, it is considered as hogging, and I'm going to have moment in this way. I've already explained the concept of sagging and hogging before. So right now hogging is negative. So right now hogging means my beam has moved upward. So as you can see here, negative means my beam needs to move upward. So right now negative is upward while my positive is downward. So following the actual concept of sagging and hogging, I have shown how the beam moves. In sagging, my beam, which is positive means sagging, my beam moves downward, so bending moment is drawn downward, while hogging means negative and my bending moment and my beam moves upward, so negative. So now for my member BF, for my member AB. So let me do it firstly for my member AB. For my member AB, I have found my bending moment to be equal to, bending moment at A is 0. Then I have minus 0.5625 and minus 4.5. So let me draw it directly in this way. At somewhere in the middle, which is at a distance of 1.5, I'm going to have minus 0.5625. This is going to be minus 0.5625, and finally at here it's going to be minus 4.5. Minus 4.5. It's also going to be negative. So now finally for a member BF, I have my For a member BF, I have my bending moment as at F it is minus 78. At F it is going to be minus 78. So negative is upward. Upward means in this direction. So right now I am observing my beam this way. So this is up. So you can see this is going to be upward, downward in that way, or you can simply you can put that way. So right now this is my member BF, and upward is this way. So I am putting my negative upward. So right now at F I have minus 78 kilonewton per meter, minus 78 kilonewton per meter. Then at E I have minus 90, and again it inside the minus 90. E is at the midpoint, so this is my E. At E I have I have minus 90, and it is going to end at minus 90 only. So how I am going to join this curve? Am I going to join it parabolically or linearly? So as you can see here, my nature of the graph is into x, which means it is linear. So I am going to which is linear. So I am going to join it linearly in this way rather than parabolically. So you need to understand this small concept as well. So as you can see here, I have explained each and every concept step by step clearly. So the video is quite long. So I've explained each and every point as a friend will describe for your analysis of frame. So if you still have any query, you can comment down below. If you like our video, do subscribe the channel and like the video. Thank you.